All right, everyone. So today we're going to be doing 6.2, which is going to be composition of functions. So the composition of function f of x with function g of x is written as f of g of x. That's how it looks with this little symbol that almost looks like a degree symbol. And it is stated f composed with g. And you'll see it backwards as well, where it's written g of f of x. And it is the combination of two functions to form a new function. It uses the output of one function as the input for another function. F of g of x is equal to f of g of x, as you can see how it's written here. To compose, replace every x in f of x with function g of x and simplify. So, you can see here how that was done in this example. If you look through, we have f of x, we have g of x, and then we take f of x and we replace all of its x's with g of x. So we're going to go ahead and try it on our own in number 1. We're going to do our own composition. So compose and then evaluate the following functions. So this one wants us to do f of g of x. I'll actually do these in different colors so you can keep track of what's going on here. Just like that. So we're going to write out f of x all of the f of x, I'm going to leave the x blank. Okay, so I just wrote out f of x, but I left its x blank. All right, so we'll put a box there in red so you can see where that blank comes in. So I rewrote f of x, but I left the x blank. Now I'm going to replace that with what g of x is, which is x squared. And in this case, there's nothing else for us to simplify, so we can just say f of g of x is equal to x squared minus 5. Now the domain of this function is just all real numbers. There's no restrictions on that because there's no radicals, there's no denominator to worry about, no variable in the denominator, so that's as is. And then they want us to do f of g of 2. So we can take our f of g of x function, and we're just going to replace x with 2. And the answer is -1. Now something important to note here, to do this evaluation, if you did g of 2, so you plugged 2 into g of x, and then you got whatever you got, which in that case would be 4, you then plug that into f of x, you would also get the same answer. So you can do it in separate steps if you're wondering. So let's go ahead and try part B. So for part B, we're basically going backwards. So we have, oops, I'm still on the highlight pen, g of f of x. So we're going to take g of x, and we're going to leave its x blank. So g of x is really just this without its x, right? You take the x out, it's just the squared. And then we have f of x, which is x minus 5, which we're going to put in parentheses. So in this case, we can actually FOIL this if we want to simplify it. And that would be our final answer. Domain of this is all real numbers. It's just a quadratic. And if we want to evaluate it at f of 2, if g of f of 2, you can plug it in here if you want to, but I would rather plug it into this one. It's a little easier to work with in that format, okay? Factored form versus standard form. So g of f of 2 is equal to 2 minus 5 squared. So, like I said, you can use the standard form in yellow. That's negative 3 squared, which is 9. Okay. G of x. So that means we're taking the g of x function, which we know to be x squared. We're taking out the x, and we're replacing it with itself in the inside. So it's just going to be x to the 4th power. Domain, all real numbers. And then they want us to evaluate g of a. And that's going to be where we just replace x with a. So a to the 4th. And that's it. So there is your first example of some composition. All right, so continuing on with the lesson, we're going to go ahead and do number 2. We have 2 functions, and we're going to be composing them in different orders and different ways. So we're doing d of h of x. So that's going to be d of h of x equals, I keep wanting to not do that parenthesis in the right color, but you get the idea. So I'm going to take the d of x function. I'm going to leave myself a little more space than that because we're going to be plugging something pretty big in there. So I just took the d of x function and I left it to x blank because that's where the h of x function is going to go. So in that, I'm just putting in the h of x function, just like that. Now, once we have it written out, we can view it as all one new function now. So blends together, and these are like terms, and that is our function. So domain is all real numbers, and we're going to evaluate once again. D of h of negative 3 means we're going to be plugging negative 3 into this function. That's 9 plus 10. That's 19. Okay. So next one, we're doing h of d of x. So now we're basically doing this in reverse. So my h of x function is taking my d of x function. So h of x, I'm rewriting my h of x function, the one on the outside, with a box instead of its x. And then in that box goes the d of x function, which I see is x plus 3. Now, since it's going to be squared, you have to put those parentheses there. Order of operations is really important. Okay, this is the whole thing is squared, not just the 3. So we're going to have to simplify this. This is actually a quadratic function in vertex form at this point. So, I mean, it depends on how the problem is written. If it asks you to simplify or expand completely, you would want to. But I typically will use the original form. Outer inner go together, 3x is 6x. I'll typically use its factored or vertex form when I go to evaluate plugging in a number because it's a little bit easier to work with. But that's not necessary, that's just an optional thing. So we have a quadratic. Once again, its domain is negative infinity to positive infinity. No restrictions on that domain. And then we are going to evaluate. So like I said, I like to use this form. Maybe I should do it in this form when I go into evaluating. But that's just an option, okay? It's not a requirement. You will get the same answer if you use the expanded form. And that's 7. So that's how you do it. D of x. So d of x is x plus 3. So I'm going to take x plus 3 and replace the x with a box. And then in that goes another x plus 3. We're plugging a function into itself, okay? It's like those little nesting dolls, sort of. So this whole function is d of x, and it's x plus 6. And that's my final answer. Domain is all real numbers. And then they want us to evaluate d of t plus 1. It's a lot to say. Like that. So I'm going to take, once again, you can always use this trick if you like. You take whatever that function is you're plugging in, and then you're going to leave a box, and in that box you're going to put in what you're plugging in. So when I plug in t plus 1, I get t plus 1 plus 6, which I can fully simplify. Not fully, but I can simplify a little more to t plus 7 by combining like terms. And that's our final answer. Okay, so continuing on with our lesson, let's go ahead and do number 3, applications of composition functions or composed functions. So sometimes composition of functions can help us with real world problems. So we're going to see a few examples of that here. So it says a car dealer is discounting all new cars by 12%. So that's good. At the same time, the manufacturer is offering a $1,500 rebate on all new cars. So what that all means is the car dealership themselves, the business, is going to give you a 12% discount. But the manufacturer, so that's like a Toyota or Hyundai, whoever you're buying the car from, the company itself, is going to offer a rebate. So if you don't know what a rebate is basically you pay the whole cost up front and then you get that price back. So if the rebate's $1,500, you're subtracting $1,500 off of the price. Okay, so just to make sure that's clear about what's happening there, it's just like a discount of that amount, basically. Mr. Navarro is buying a car that is priced $24,500. Will the final price be lower if the discount is applied before or after the rebate, basically? So we want to see which one of these discounts you want to apply first. So if they give you the option, they say, well, you want to do the dealership discount or the manufacturer rebate first, okay, to see which one is going to get you the lower price. Obviously, you want to pay the lowest price possible. So we're going to write out functions to represent each of these scenarios. I'm going to do the car dealer in blue, and I'm going to do the manufacturer in red. So the car dealer price, I'm just going to do the price. Basically, I'm writing a function for the price of the car after the car dealership discount, okay? So I don't know if anybody's ever shown you this. Some people are really shocked by this, but basically, if you want to find out what the price of something is after a percentage discount, you basically take that amount and subtract away what that percentage of that amount is, okay? So let's say X is the entire price, the original price of the car. We're going to do X minus 0.12 times X, okay? That's like subtracting away that discount. And that ultimately simplifies to become, so this is like a 1 in the front. 1 minus 0.12 is 0.88x. So you can actually do this all in one step. So like say you go to the store and you have something that's 20% off. 100% minus 20% is 80%. You're paying 80% of the price of that item, okay? That's how much you're going to be paying. So 0.8 times the price of your item, which is X. Okay, you don't have to do two separate steps for that. You can do it all in one. So this right here basically represents the price of the car after the dealership discount only, okay? Now let's talk about the price of the car after the manufacturer discount only. So we'll call it M of X is equal to the price of the car minus $1,500. So these are two independent functions. This represents the price of the car only after the dealership discount. This represents the price of the car only after the manufacturer's rebate. But we're going to be getting both of these deals, okay? So we want to compose them. So we're going to do it both ways. We're going to first compose C of M of X. So that's going to be where I take my C of X function and I'm plugging, remember the box, replacing the X with a box, but I'm not going to do that here. I'm just going to jump right in with the M of X function. Distribute. Okay. So that's the formula for when we do the, basically we do C of M of X, okay? So now we're going to do it the other way around. So that's going to be M of X, but we're replacing it with C of X. All right, so let me make this clear, right? Because it is a little bit confusing at times. Box these in so we know these are the final equations that we're working with. Apparently I can't do that right now very well. I guess I wrote on an angle, so never mind. So this one right here represents where you take the car dealership discount first, and then you do the manufacturer's discount, okay? Car dealership discount, then the manufacturer's discount. This one up here means you did the manufacturer's discount first, then you do the car dealership. So you work inside out. Now to tell which one's going to be cheaper for our particular situation, we're going to have to plug in $24,500 into each of these equations, okay? So I'm going to kind of do it off camera here because we don't have a lot of room. So I'm just going to do C of M of whatever we're plugging in, which is $24,500. So let me just do the calculation. So that means all in all, in that case, you're going to be paying $20,240 if you do the manufacturer first, then the car dealership. Now let's say we went the other way and we do the car dealership, then the manufacturers. So 0.88. We get 20,060. So of course, you're going to go with the cheaper option, which is going to be this one right here. So if you do the car dealership discount first and then the rebate, you're going to get a better deal than going the other way around. So that's how that works. So this one says, Kohl's is having a holiday sale. Each item is on sale for 30% off the original price. Then the additional 10% off is taken on the sales price at the register. So let's say the 30% off we're going to do in blue, that equation or function. Then the additional 10% off the sale price at the register is going to be in red. Let X represent the price of the item. Is it better to apply the sale price before or after the additional register discount? Justify your answer. So, I don't know, we'll do the first one as f of x, and we'll do the next one as g of x. So f of x is equal to, if you're taking 30% off the original price, you're paying 70% of the price, right? 100 minus 30%. So 0.7 times x is going to be the price after 30%. Now, if you do g of x, if you're taking 10% off, you're paying 90%, okay? All right, I'm just making sure I'm still recording. So, let's see which one we should do first. Where did my pen go? Oh no. There we go. Okay, I got my pen back. So let's do f of g of x. Basically, that's where we do the g of x first, then the f of x. We always work inside out. So we're going to take the f of x function, and we're going to replace its x with g of x. And that's just going to be the product of those two things times x. So, and you can write 0.70 as 0.7. It's the same thing. So 0.7 times 0.9, that's 0.63. So you're basically only paying 63% of the price of the item after those two discounts. If you do the g of x first, then the f of x. Now, if we do the opposite, g of f of x, that's going to be the g of x function times the f of x function. And you're going to notice that these two compositions come out to be the exact same thing. And that's because it's just, these ones are strictly multiplication based. Multiplication is commutative. So it actually doesn't matter which one you do first when it comes to two percentages. So just a tip in life, if they offer you 2% discounts and they say, which one you want to do first? I don't know if they asked you that or not, but it doesn't matter which you do first with a percentage based discount. Okay. It doesn't matter at all. So there you go. All right, so for the last problem, it says the number n of bacteria on a refrigerated petri dish is given by n of t is equal to 20t squared minus 80t plus 500, where t represents the temperature in degrees Celsius, with 2 is less than or equal to t is less than or equal to 14. So that means that t is somewhere between 2 and 14 with those bounds included. When the petri dish is removed from the refrigerator or refrigeration, the temperature of the petri dish is given by t of t is equal to 4t plus 2, where t is the time in hours, with 0 less than or equal to t is less than or equal to 3. So what that all means is we have a function that represents the number of bacteria in a petri dish when it is being refrigerated between 2 and 14 hours, where t is temperature. Big T represents degrees Celsius, so between 2 and 14 degrees Celsius. And then we remove it from refrigeration, and its temperature between these hours in time, 0 to 3 hours. So compose a function that shows the number of bacteria in the petri dish t hours after being removed from the refrigerator. Okay, so compose a function, the number of bacteria in the petri dish t hours after removed from the refrigerator. So that's going to be n of t of t. Okay, that's the composition that we have to do if we're doing the after being removed from the refrigerator. Okay, so that's going to be, we're going to take the n of t function and we're replacing all of its t's with the t of t function. Okay. That's all I did there. So now we are going to simplify that. So we're going to have to square this using FOIL. And distribute 80 times 4. 320. Okay. And then I'm going to combine like terms inside the parentheses. Distribute 20 times 16. And then combine like terms. These are going to cancel out. These are going to combine. And that's our final answer. So that's the function that basically represents the number of bacteria on the petri dish T hours after being removed from the refrigerator. Okay? Because it's in the refrigerator and then it's taken out of the refrigerator. So in the refrigerator, it changes the rate of which the bacteria live, basically. Okay, which kind of makes sense because duh, you refrigerate your food. Okay, for a reason. You don't want bacteria in it. The fridge basically stops from as many bacteria growing. Okay, when we take it out, grows at a different rate. In most cases, there are some bacteria that, this is getting off on a tangent, but you get the idea. So, state how much bacteria are present on the petri dish 1.2 hours after removal from the refrigerator. So we already did the formula for this. We already came up with the formula that represents after removal. So all we have to do here is take this amount and plug it in to that function. So that's how much bacteria is there after that time. Doesn't give us a units for that. Okay. So the next one says, state when the bacteria count will reach 2,500. So we have a formula for the bacteria count in terms of time. And we want to know when that time will equal 200 or $2,500. 100, not $2,500. When the count will reach 2,500 bacteria. So we're going to set it equal to 2,500, and then we're going to solve for t. I don't know what the square root of this is. Hang on. I gotta get my calculator. Okay. When you're using the iPhone calculator, you have to turn your lock off to be able to do this. So there we go. At approximately 2.55 hours. So almost 3 hours is when you will reach that amount of bacteria. So that's how you do it. And good luck with the assignment. I'll put some comments in. So yeah.